Moving on to part 2 of chapter 7-4, properties of similar triangles. And we're going to look at the transversal proportionality corollary, which is just another name for theorem definition, and triangle angle bisector theorem. That's a whole mouthful of words. But let's get right to the two transversal. Now, this one is kind of just following along what we just previously did, but we had triangles. Here we have 3 or more parallel lines. Now that 3 or more is important. We got to have 3 or more parallel lines. I could have a lot more here if I wanted to. And what happens is, given two transversals, it divides up these sections right here, this one and this one, proportionally to its other opposite side over here. Now in this definition we have segment AC, this segment right here, over CE, this segment here, is equal to BD over DE. So if we call that X and Y and then Z and I guess W, we would have X over Y is equal to Z over W. And a lot of people write it like this, and you're going to see test and quiz questions with it written like this, but just think how these segments are broken up. So there is more than one way to write this though. Now the key to this problem in setting it up is to make sure you use corresponding comparisons on your ratios. If I have, here let's go to X, Y, Z, and I guess I got to put W over here. A little bit, that's a horrible W. So here we go again, W. Now if I put X over Y, I got to make sure that my ratio, when I set up the proportion, has a corresponding part over here. So if I have the X here, the Z better be over here. See how this corresponds? And the W is over here. So I can write it in more than one way. So let's go ahead and try it a different way. Let's just say I want to start off with the Y. And I want to put it over W. Well, look what I did. I put that over that, so I better put that over that. Do not put Z on top, because this corresponds to that, that corresponds to that. This Y does not correspond to that Z. That would be a no-no. So you have a little bit of flexibility how you want to set this up. And this comes in very important when we're doing some algebra problems, because very often it is in our benefit not to put the X on the bottom. So let's take a look at this. Here we have an X. We don't know what it is. So we got an algebra problem. I need to set up a proportion. Now these lines are parallel. We got to have that. And that means this and this is proportional. When I compare this ratio to this ratio, they're proportional. Well, I want to put my X on top, so I'm going to compare the X over 20. And the corresponding to X is the 9, way over there, to 15. So I'm going to simplify this. Well, I always like to work in smaller numbers as possible. So I'm going to simplify this. Well, 3 goes into that 3 times. That goes into 5, so out goes that. I got 3/5. Use my cross product, so I have 5x is equal to, and 60, right? So x is equal to 12. Now I could have done it a different way. Watch this. I could have put x over 9. I corresponded with this. That means I better put the 20 on top over here. 20 over 15. And again, I can simplify this. 5 goes into both of those. That goes in at 4. That goes into at 3. That way I don't have to worry about big numbers. So I got 3x. And 4 times 9 is 36. Well, guess what? X still equals to 12. The danger is, do not mix the corresponding parts up. I can't put 20 over 9 and x over 15. That would just look a little odd. And I would get some unusual answers too. Decimal answers. That would be a no-no. Even though you can get a decimal answer if I wanted you to get one. Well, that doesn't make sense. So let's go on to the next example. All right. Now, since we can put these things in different orders, a good technique, something you don't have to do, but it makes the problem work a little faster, is try to avoid putting your x's in the denominator if you have multiple variables. Like I wouldn't want to put x over 3x minus 2. I just have to work a little bit harder at that. Even though cross multiplication, it knocks it out fairly quick. So I'm just going to do this. I'm going to put x over 3. And I'm going to put this on top because that corresponds. And 6. Cross multiply, so that's going to be 6x. And I have 3 times 3x. I'll go ahead and go and write it out for you. I want to distribute. See how I'm distributing? So I have 6x. I could have divided by 3 too on both sides. That's something that I want you to start thinking about for Algebra 2. And I am going to subtract 3x on both sides and add 6. So I'm going to have 6 on this side. And I'm going to have 3x on this side. And guess what? X is equal to 2. All right? Bingo. Moving on. So let's take a look at the triangle angle bisector theorem. Basically what this theorem is saying is an angle bisector, which is right here. See how these two angles are equal? That means this line bisects these two angles. It does not bisect these two lines right here. That would be a no-no. Don't assume that. These two lines are going to be different lengths. So what it does is that it makes these proportional to its sides. It makes the segments, it cuts these two segments in parts to where these two parts are proportional to its sides. Here we have AB, and we have BD, DC, and AC. So this is how they set it up. They went ahead and did BD over DC, this over that, is equal to this over that. So what we did was we set up our corresponding sides. This corresponds to that, that corresponds to that. Another way you could do it is do this over that, BD over AB is DC over AC. Okay, that's another way to do it. And it just depends on what kind of algebra situation you have and what strategy you want to figure out what you're trying to solve for. Later on, when we get into more advanced work, I'm going to show you another method to where we can actually use multiplication to solve a proportionality problem to where we have like two variables, an x and a y here, but we know the whole length. That's real cool too. So let's take a look at this example. Here we have an angle bisector. We know that because this and that. There won't be any instructions on that. I'm not going to say it's an angle bisector. You have to recognize that it's an angle bisector. These are not equal, obviously. That's a 3 and that's a 5. So we're going to set up a proportion and solve this. There's more than one way. I could do 15 over 3 is equal to 4x plus 1 over 5. I could do 3 over 5 is equal to 15 over 4x plus 1. I think it just doesn't matter. I'm just going to go ahead and do it this way. I'll do 3 over 15. Oops, I probably didn't want to do that, but that's okay. Because look, 5, it works out. With only one variable, it doesn't matter if it's on the top or the bottom. And I'm just going to cross multiply. And I get 3 times 4x plus 1, a little bit of bleeding, is equal to 5 times 15. And yuck, I hate that bleeding. So I'm going to distribute. So I get 12x plus 3 is equal to 75. I'm going to subtract 3 on both sides, so that gives me 12x is equal to 72. And 6 goes in, 6 times 12 is 72, so x is equal to 6. Now this makes sense because look, here's 6. I'm going to plug 6 in to find my geometry answer. That was just my algebra answer. So 6 times 4 is 24, so this whole side is 25. This kind of feels right because look, 15 is to 3 as 25 is to 5. Kind of makes sense, doesn't it? 15 divided by 3 is 5. 25 divided by 5 is 5 as well. So the proportion is very sound. Alrighty, this went a little long, but these two lessons are important and you have to be a little bit more disciplined when tackling these things. I strongly suggest you go on a blank sheet of paper right now, go back and look at these two examples, work them, and check your work.